Thank you very much. As you conclude, it seems that a lot of things are going on parallel in this area of combining the SCADA challenges and the academic side. So thank you very much, Professor Shukla. And our next speaker going to be Professor Don Song. Don Song is a professor in the Department of Electrical Engineering and Computer Science at UC Berkeley. Her research interest lies in deep learning and security. She has studied diverse security and privacy issues in computer systems and networks, including areas ranging from software security, networking security, applied cryptography, to the intersection of machine learning and security. Professor Song, it's our pleasure to have you here.
Okay, hi everyone. Thanks for being here. My name is Don Song. I'm a professor at UC Berkeley. So today I'll talk about one of our projects on secure and privacy-preserving data analytics and machine learning. My group does a lot of different work in the area of at the intersection between AI and security. And today I only have time to talk about one of the projects. And tomorrow I'm also giving a talk at the AI conference on some of our other work, including adversarial deep learning and some other topics at the intersection between AI and security. Okay, so this work is joint work with my students, Noah Johnson Jr. and collaborators Joe Hallerstein. So what's the problem that we are trying to solve here? One of the really big problems in the big data and also machine learning is that today we have a huge amount of data, but a lot of this data is sensitive. And because of this, a lot of the value is actually being locked in because people don't have secure and privacy-preserving ways to analyze this data. As a consequence, the value of this big data is now being utilized. So the question is, how can we do this? So again, this is a more detailed problem overview. Is that here we have valuable data that's being siloed and underutilized for security and privacy concerns. We could be getting a lot of business intelligence insights from the data, and also even for security applications. But on the other hand, if we don't do this well with the security and privacy, then privacy breaches and data exfiltration, all these can be issues. And as we all know, security and privacy risks are real. And there are lots of severe consequences for data breaches, and there are, again, lots of real-world incidents for data breaches. So then the question is, what can we do? What kind of solutions can we offer? So one solution people have proposed in the past is anonymization. Unfortunately, as we know, that anonymization is ineffective. So for example, there has been real-world examples, for example, with the Netflix data set where Netflix released some of their anonymized movie review data, and also with this New York City taxi data where anonymized taxi trip data has been released. But again, in both cases, researchers have shown that you can combine the released anonymized data with other public data to de-anonymize users. And hence, anonymization is not a sufficient solution. And another solution that people typically use is, for example, access control. But however, all these existing solutions, they are insufficient. So for example, for access control, it's an all-or-nothing approach. So either you don't get access to the data at all, then in this case, you just cannot use the data at all. Or if you give access, for example, to some employees or to some analysts, then that person has all the access to the data, including seeing the raw data. And in this case, you can have insider attacks, or the person's account may be compromised. Then again, this then does not provide any protection to the sensitive data. And also, as we mentioned, for anonymization, one is that it provides insufficient protection, and also once you anonymize the data, also the value of the data has been decreased. Oftentimes, you can destroy data utility. So then the question is, again, what can we do? How can we solve the problem better? So in our project called ALLEGRO, we propose a 3-in-1 solution for secure and privacy-preserving data analytics. So in particular, we have 3 components in ALLEGRO. Privacy-preserving general data analytics. We support general analytics, but at the same time provides privacy protection. And privacy-preserving machine learning, where we support machine learning, again, with protection of privacy. And also, we enable fine-grained access control and auditing capabilities. So in this talk, I won't have time to go into everything. And also, some of the work is still work in progress. I will mainly focus on the first aspect, privacy-preserving data analytics. And one important usage scenario for our project ALLEGRO is that we want to be able to deploy the system in a very easy way so that you don't need to change the existing workflow, and also you don't need to change the existing, for example, backend data store and so on. So in particular, what we do is that the analysts will still do their typical workflow where they write their analytics program, for example, to post their queries. And let's say we have some security and privacy policies that we want to enforce. So in general, what ALLEGRO does is that ALLEGRO actually will transform the original analytics program into a secure version of the analytics program. And I'll talk about this in a second in more detail. ALLEGRO, in this case, uses a rewriting approach that rewrites the original analytics program into a secure version of the analytics program that is guaranteed to satisfy the security and privacy policies. And now the secure analytics program can then be run on the existing data store in the backend data store or database or your big data compute frameworks. And in this case, again, you don't need to change the analyst workflow, and also you don't need to change the backend system. And now, the backend system, when executing the secure analytics program, will then will automatically generate secure and privacy-preserving program results and send back to the analyst. As you can see here, the advantage of ALLEGRO is that one, it still enables the analyst to do his or her job, meaning it can still analyze the data and extract value out of the data. But on the other hand, ALLEGRO, in this case, can ensure the security and privacy policies. And also, ALLEGRO is designed to support a variety of different types of security and privacy policies. We have some built-in security and privacy policies, including, for example, differential privacy. And also, there's another aspect that I won't have time to talk about, can enable SGX security analytics as well, and also other policies. And the users can also support custom policies via a rich policy language. So with this approach, ALLEGRO achieves a number of advantages. One is that this actually provides formal security guarantees, and also is compatible with any standard database data store, and supports general data analytics and machine learning. And also, in this approach, it's transparent to the analyst. So the analyst doesn't even need to know about how to do secure and privacy preserving analytics or machine learning. The system actually does it for the analyst. So again, in this talk, due to limited time, I will just focus on one aspect of the system, how we actually enforce differential privacy as a security and privacy policy. So just a few words about the differential privacy very quickly. Differential privacy essentially is a notion, it's a very powerful notion for providing privacy for these data analytics. And in a sense, it provides a formal guarantee of distinguishability. In particular, in this case, we want to compute a differentially private query F. And we see that this computation F is differentially private if F satisfies the following property. So in this case, we consider one data set, the original data set, and another data set which is called a neighboring data set of the original data set, which only just differs by one data point to the original data set, meaning either one data point is added or removed or changed. And we say the computation F satisfies the differential privacy if the computation result of F from these two data sets, the original data set and the neighboring data sets, are almost the same, meaning you almost cannot distinguish the results, the two results. And this is a notion of differential privacy. And in this case, what is the differential privacy says is that essentially, because the computation F cannot distinguish between these two data sets, the original data set and the neighboring data set, then in this case, and hence you can see that the user's privacy is being protected because the computation itself cannot even distinguish the two cases. And there has been growing interest from industry on differential privacy. For example, both Google and Apple have recently released their deployed differential privacy in certain parts of their products, including for Google, it's the browser site collecting information from users, and for Apple, it's the smart, it's the keyboard usage. So then, so differential privacy is a very strong notion and gives you theoretical guarantee about preserving users' privacy. Then the question is, how can we achieve differential privacy? And there has been different privacy mechanisms proposed. Essentially, one approach is to add random noise to the query results that is scaled to what's called the query's sensitivity. And again, I won't have time to go into the details how the sensitivity is actually computed. So the main challenge is how can we actually enable differential privacy in practice in the real world. Even though I mentioned Google and Apple have deployed differential privacy in their products, but these are actually, unfortunately, one of two of the very rare cases where differential privacy has been used in practice, and also in both cases have been used in very narrow parts of the products. So there has been a lot of work done in differential privacy, but unfortunately, most of them is theoretical in nature and has only been evaluated on very small scale and synthetic data sets. And the question is, how can we actually take the next step to actually enable differential privacy in practice? And in particular, the current approaches are not, for differential privacy are not designed to support real-world requirements, including performance, scalability, compatibility with existing data systems, as well as flexible access for analysts. And again, this is a table of different general-purpose differential privacy mechanisms, including the bottom row is a new differential privacy mechanism that we have proposed called elastic sensitivity. So each of these mechanisms has its own unique strengths and limitations, and they may be particularly suited for different types of analytics, data analytics queries. And most of these actually do not are not compatible with the existing databases. So our goal is that we want to actually be able to support general purpose differential privacy mechanisms, again, in a way that's make it very easy to deploy and very easy to use. Unfortunately, with the previous approaches, if you want to use these different differential privacy mechanisms, you actually would have to go through a lot in terms of you have to change the existing database and data stores, and you actually often have to have replicated databases to be able to use these different mechanisms. And this is not practical. So all this, the limitations of the current approaches motivated us to propose a new solution called intrinsically private queries. And we enable this intrinsically private queries through our query rewriting, our program rewriting approach. In particular, an intrinsic private query as a query which already has a privacy mechanism built in, and hence the query itself automatically enforces the differential privacy guarantees on its results. And this is the notion of the concept of intrinsically private query. And the advantage of intrinsically private query is that one, again, it does not require custom runtime or database modifications, and also it's a very flexible mechanism, can support all existing differential privacy mechanisms. And again, as I mentioned, this intrinsically private query is enabled through our query writing mechanism. And I won't go into the detail. Here's one example showing how our elastic sensitivity mechanism can be supported using a query writing mechanism that rewrites the original query on the left into the right-hand side, which actually enables the elastic sensitivity privacy mechanism, which supports different aspects, including sampling, different sampling mechanisms, and also adding the noise perturbation. So again, comparing to the previous approaches, where in order to deploy these privacy mechanisms, you would have to change the backend databases, you would have to replicate the data store to support different mechanisms. With our approach, through this query rewriting, again, it's very easy to deploy these different differential privacy mechanisms. The analysts only need to just write the original query as before. Again, the analyst in this case doesn't even need to know about differential privacy at all. And our ALLEGRO system will then automatically rewrite the query into this intrinsically private query. And then this intrinsically private query gets executed on the original database. Again, the original database doesn't need to be changed at all. And this execution will then provide differentially private results automatically. And again, the advantage of this approach is that we can, using this approach, we can support any standards backend database engines, and we provide unified support for a wide variety of differential privacy mechanisms, and this can very easily integrate with existing data pipelines. And inside the ALLEGRO system, in order to support this automatic query writing to enable intrinsically private queries, we have to essentially develop a number of different components. We need to be able to automatically analyze the original query to using our analysis engine, so that we can actually analyze the sensitivity of the original query and to figure out essentially how much noise to add, how much perturbation to add to the final results. And also we have a system for privacy mechanism selection, where it actually uses a machine learning model to figure out, because for different queries you may need different privacy mechanisms that can be best suited for this particular query. Then this machine learning model from the features from the original query will then figure out which privacy mechanism is the best, and then select that mechanism. And then we have a transformation engine that will then transform the original query into the intrinsically private query using the particular privacy mechanism that's being selected. Okay. So we've built a system and have done experiments, and in particular in this case, we actually have a collaboration with Uber, where we actually, for the first time, we actually analyzed millions of queries and analyzed the utility of our mechanism over huge, very high number of queries. I won't go into the details, but the results show that with our approach, for a majority of the queries in the real world, we can actually provide very good utilities and also at the same time provide privacy protection. And our mechanism selection can select the best query, the best privacy mechanism for the query. And to summarize, then so far I've only talked about the differentially private query analytics queries, but also we use a similar approach for differentially private machine learning, and some of this work is still also work in progress. And similarly, we use a similar rewriting approach to enable fine-grained access control and auditing. And again, as I mentioned, so some of this work is actually being piloted at Uber, and for the first time, actually enabling differentially private queries on real-world queries. Yeah, okay. So to summarize, we hope that using the system, we can enable a secure and privacy-preserving data analytics and machine learning to unlock the value of big data while eliminating the risk of data and privacy breaches. Yeah, thank you.